Okay, so welcome back. This is our second video about map and MPE inference. So let's continue with the MPE variable elimination algorithm. And now we're going to do a step-by-step example using our example network here. So these are the probabilities and also the network. So the first step that I'm going to do is to convert this Bayesian network into a Markov network using the moralization process. So I'm going to replace also this notation here that we're calling theta s given c or theta t1 given c by another notation that we use phi, that is more general, just to say that is a factor mentioning these variables. So here we have the moralized graph here, and we have the tables now only mentioning the factors. So this process will work equally well for Bayesian networks and for Markov networks too. We have an elimination order that is SC, A, T1, T2, and it's gonna do the variable elimination, just replacing the maximization, just replacing the summation by maximization. So the first step we have to do is to take all the factors that mention the first variable that we're going to eliminate. So the factors that mention the variable s are this factor here, phi1, the factor phi3, and also the factor phi4. So three factors mention the variable s. So I'm going to multiply two of those factors together, and later on we take the result and multiply by the older one. So we need to multiply all the three factors. Alright, so we started by multiplying phi3 by phi4 and getting a new factor. So we're going to call this sigma 1. And the process of multiplication is the same that we have discussed it several times. So we will not go through this. And we have this new factor phi1, sigma 1, that mentions variable t2, s, and c. So I'm going to take this factor sigma 1 and I'm going to multiply it now by this factor here, phi1, and get a new factor. So this is the new factor. Again, multiplying sigma 1, phi1 by sigma 1 and getting now what we're calling sigma 2. Again, the multiplication will mention the variables t2, s, and c. Okay, as no other factor mentions variable s, what I'm going to do now is to eliminate the variable s using maximization. So this is the process. So we have this factor sigma 2 here that are going to maximize out the variable s. Good. The process is very simple, very similar to the summation. We take the matching assignments here for C and T2. So we have this yes and positive. I'm going to have another yes and positive here. So I'm going to match these two rows, and we see that they have the two possible values for variable s. I'm going to maximize this. So the maximum between 0.0220 and 0.0043 is going to be 0.0220. So we have this guy here, right? And I keep in doing this. See that I eliminating the variable s, but keeping the matching assignment between the other variables. And we do this for all the 8 rows, and we have now a smaller table that does not mention s. We can discard all the tables all the factors that we had before. So we discard these. We also discard the sigma 1. We also discard the phi 1 and 3 that we multiply together, I guess the phi 4 too. And we're going to just keep 3 factors. This tau 2, this phi 2, and this phi 5. We're going to continue eliminating the other variables. Alright, so we have these 3 factors, and now the next variable to be eliminated is variable c. And if you look at the factors that mention variable c, we have one here and one here, just 2. I'm going to multiply them together and eliminate the variable c. So here we are. So we are multiplying the tau 2 factor by the sigma 2 factor. Again, this is a normal process of a multiplication of 2 factors, the join operation that we have implemented in the tutorials. and not to go through this. C, T2 are mentioned here, C and T1 are mentioned here, so the new factor that sigma 3 will mention these three variables, C, T1, and T2. So now we have a larger variable. But now this is the only factor, we can discard this and this. This is the only factor that mentions variable C. I'm going to eliminate the variable C by maximizing out. So here we are, we needed to eliminate this variable C here. So we take the matching assignments. So we're going to have V and V for these two rows here. And we look at what is the maximum value. And we have here 0.0176 and 0.0209. The maximum is this guy here that's going to be transferred to this. And we keep on doing this for all the rows. We're going to now have a smaller table that does not mention a variable C anymore. We can discard these, and now we have only the variables A, T1, and T2, and A is going to be the next variable that I'm going to eliminate. So here are the only two factors that we still have. It's tau3 and phi5. I'm going to eliminate the variable A now. Okay, so to eliminate the variable A, we do not need to multiply any factors because A only happens here. That's good. So we go directly to the process of eliminating the variable A by maximizing. So this is the process. So again, what we're going to do is to look at matching assignments here and here for the variables that we are not eliminating. So these are the two rules. See that we operate all possible values of A and take the maximum between these two rows. So we get this new table here. I'm calling this the tau4. And the tau4 mentions variables T1 and T2 because variable A was eliminated. Now I discard these. We have these two factors, tau3 and tau4. And they only mentions variables T1 and T2. We're going to eliminate T1 first and T2 later. Alright, so these are the two factors. Let's start with T2. We need to multiply because T2 is happening here and is also happening here. So we have to multiply these two factors together and eliminate T1. So here we have the multiplication of the factors. It's very simple because this factor tau4 only has values 1. So we're going to match here and we have the same table that we had before. I'm calling this table the sigma 5. So then we go from sigma 5 to tau 5 by a maximization process again that we're going to eliminate the variable T1. That's it. So I'm going to remove T1, this guy here. So I'm going to take the matching values for T2 and I'm going to maximize out. So we're going to see that this is the maximum value and also this one is the maximum value. So they will go to this variable here. So we see that we are eliminating all the variables, all the Q variables, and we're going to end with one trivial assignment that has only one value that's going to be the value of the MPE query. So it's going to be the next step when we eliminated the variable T2. So in this case here we have the value T2. This tau5 is the only factor that remains. I'm going to eliminate this factor too by maximizing out the variable T2. Basically going to take the maximum between the two rows here and I'm going to have this new factor here that has no variables at all and has just the value 3390. We can call this the tau6 and has no variables in its domain. So that's going to be our answer. So 0.3390, as we saw before when we computed the joint distribution over all the variables, that this is the assignment with the highest probability. Notice that we know the probability of the map of the MPE query, but we don't know which is the assignment, right? If it's male or female and so on. So what we need to do is to track down. So we know, for instance, that the maximum value for T2 came from this not VE here, right? So where this value came from, but we lost the values that were before that, right? So we need to recover this. And we're going to discuss a technique for doing that in a few slides. Okay, so we got the answer for our MP probability query. So this is the value, but we lost the instantiation, and we need to recover that information in some way. So we need to store this as we eliminate the variables. There are many techniques for doing this, and we have implemented in one of the tutorials one technique that basically traces back all the computations and finds where the assignments came from. But now we're going to implement a new technique that's going to be easier. So this new technique has two variations. One variation is that we create an additional data structure that has pointers, and we point to the path that we came from. So basically we can trace back the pointers and see what was the correct answer for the MPE instantiation. What we're going to do in this lecture, we will expand the factors to store this information. So you have one extra field that we can put this information. Let's see how it works. So the technique that we're going to discuss to recover the MPE instantiation is called the extended factors. It's basically adding one new field. So usually to have these tables here, we're going to have one table that has this additional field here. We're going to use this notation here, that's phi x between brackets to denote what is the instantiation, and we keep this phi x between parentheses to denote the probability, the number that we have in the table. So the technique is actually very simple. We're going to take note where the maximum value came from, right? When we are eliminating one variable. So for instance, we are eliminating variable s here. So instead of discarding the information of s completely when we maximize out this variable, I'm going to keep the information what was the instantiation that gave origin to the entry with the highest probability. So for instance, here we're going to match this guy here with this guy here. So both have the same instantiation, yes and true for the test. But this guy here is male and this is a female entry. And the one that has the highest probability is this one compared with this one. So this new entry here that does not mention S only mention C, yes, and T2 equal to a positive test, a positive V. It has the probability 0.0220 equal to this one, and the value of S that gives origin to this instantiation was male, right? And we keep on doing this. So when we compare this guy here with this guy here, we know that this one 0.0055 is larger, so we're going to store male here. And when we compare this 0.1045 with this 0.0228, we know that this guy is larger, so this male corresponds to this one. And finally, when we compare this one with this one, we know that this one is larger, so this female goes here, right? So basically taking note of the instantiation, the value of the variable that we are maximizing out, what is the value of a maximum probability. So what we're going to have to do is to modify the maximize out operation in order to save these entries, but we will also have to modify the join operation a little bit only, because the join operation will have to carry this information forward, right? So I'm going to have this information. It will not modify it, but we will need to modify it slightly to have this information passed forward to the next entry. So to the next factor. So let's again run one example step by step and check our understanding. Good. So again, I'm going to use the same example, but and not to make exactly the same computations again and again, I'm going to change it slightly by introducing a piece of evidence that's going to be A equal yes. So this variable here is going to be observed, and the value for variable A is going to be yes. So again, the same process. We're going to convert the Bayes network into a Markov network and through the process of modernization, and we're going to start eliminating the variables. So now we transform it. We have these factors phi1, phi2, phi3, phi4, phi5. We're going to introduce the evidence by eliminating all the rows that do not match the evidence. So these are the rows that have A equal null. So now I have this guy here. Good. And we can now start with the elimination process. The elimination process will have the same order that we had before. So I'm going to start with S and C and T1 and T2 and A. So we're going to eliminate all the variables. So I guess S, C, A, T1, T2. And at the end, let's take a look at what is the instantiation. So good. So remember that when we start with variable S, we need to multiply three factors. One is phi3, the other one is phi4 that we are already multiplying here, but we also have to multiply the phi1. So we have the first factor that is sigma 1, and I'm going to now multiply sigma 1 by phi1. Take a look at that. Nothing changed so far, right? Because it will only change when we maximize out the variable that we need to save the information of where the value of maximum probability came from. So for now, everything is equal to what we had done before. Next slide. Then here we are multiplying the phi1 by the sigma 1 that we got from the previous slide, and now we have this sigma 2 here. Now we are in position to eliminate the variable S, so we can discard this guy, and also the phi, don't remember now, that's what's phi 4 and phi 3 that multiply it, and we're going to keep only these three guys here. That's going to be the phi 2, the phi 5, and the sigma 2. And now we're going to maximize out sigma 2, eliminating the variable S. So this is the process. So interesting, yeah, it's the same example that we had in the slide. So we are removing this variable here. That's good. We take a look at the entries that match. So these entries here match. The maximum is this guy here. So I'm going to copy here. And so we have this value here. And we know that this is male. So male here. And we keep on doing that. So we are saving the information. And now we have this extended factor tau2 here that has not only the probabilities, but also the instantiations. And now we're gonna move on with the process, and the next variable that we're gonna eliminate is C. Okay, so we continue the process of eliminating variables, and now we're gonna eliminate the variable C. We look at all the factors that mention variable C, and the factors are the tau2 that we have just generated, and the phi2 that it is one of the original factors that we have in the Bayesian network. And we're going to multiply those two factors together. But we need to be a little bit careful when we do this. We have to make a small change into the join operation in order to carry the information of the instantiations in the correct way. So what I mean is that when we multiply this entry here by this entry here, we generate this entry here. And the probability that we have here is just the probability that we have here and the probability that we have here. So we have this multiplication, but we need to carry this male here, that is instantiation, to this place here. And see that we're going to copy this also male information that we have in the first row of the tau2 factor to the second row of this sigma 3 factor 2. Because when we multiply this guy here, let me just erase what we have here. So when we multiply this guy here by this guy here, what we have is an entry that has yes. For T1 it has not V, and for T2 it has V. So exactly this entry here. And in this case, the probability is going to be the multiplication of this 0.0220 by 0.20 that we have here. So we have this probability here. And we need to also copy this information went to here, but we also go to here. So we need to make a small change into the factor multiplication operation that we have in order to correctly copy the instantiations for the variables that we are eliminating in the correct way. And also when we multiply, we need to also copy this information correctly. So as we multiply these two factors, these are the only factors that mention variable c, and now we have only two factors remaining. The only factor that mentions variable c now is this guy here, the sigma 3. We are in position of eliminating the variable c. When we do this, we need to take note of the values of maximum probability for c that were eliminated. So here we have, this is the sigma 3. We're going to eliminate the variable c, so I'm going to take two matching assignments for all variables, not c, and we see that we have yes and no here. We take the maximum. The maximum is this value compared with this value, and so we're going to take this information that we have here, that is no, and put this together with the male in this entry here. So basically we are saying that this probability 0.0209, it has the assignment S equal male and C equal no, right? And we keep on doing this. So when we take this guy here and this guy here, we look at the maximum one between these and this, it's clear that it's going to be this guy here. So this is the probability that we have, and we take also the instantiation no here and complement with a male. So we have male and no, and we keep on doing this, right? So every variable that we eliminate, we need to append the information of that variable that we are eliminating, the values that gave the highest probability, and we need to append it to the new factor. Now we have the factors that mention only the variables t1, t2, and a. Actually, a is not a variable anymore, it's just a value because it was evidence. We need to eliminate the next variable that's going to be a. It's going to be a very simple process because a is not a variable anymore, but we're going to remove a from the table. So this is the process. Depending on how you implement your operations, you may not even need to have this step. So possibly when you observe the evidence, if you observe and automatically remove the column, you don't need to have this operation. But if you don't do this, and in the tutorials we do not, when you observe evidence, we do not remove columns. So in this, if you are following the code that we have in the tutorials, we need this extra step here. So again, it's going to be a maximization process, but we have just one entry here. So we're going to take this entry and put it here and copy this value to here. So it's going to be a one-to-one elimination, just dropping this information here. Notice that as we don't have any instantiations here, there is nothing to copy. So it's like having an empty instantiation passing through the factors. Now we have variables t1 and t2 in this factor, and t1 and t2 in this factor, and we're gonna eliminate the variable t1. So we're gonna multiply together and eliminate. So again, multiplying the two factors. In this case here, we generate a new factor that is sigma 5. Mention the two variables because we have this deterministic CPT here. It will make that these two probabilities here become 0. And again, we are just doing the join operation, so we are carrying the information about the instantiations forward. There is nothing to do here. In the next step, we need to eliminate the variable t1. So this is the process of eliminating the variable t1. Again, the same process before. Because we are eliminating t1, we take matching assignments for t2. I take the maximum, in this case it's going to be this guy here, so I copy this information to here, so we have this probability, and we carry the information, so T1, we have this positive VE here, we keep the positive VE here. And for the other two entries, we have 0 here and 0.3390. Again, the maximum is going to be this guy, it's copied to here, and this guy had this negative VE here that is copied to here. So we eliminated T1, and the last step will be elimination of T2. And this is the process of eliminating T2. We have, again, the last step. We take the maximum between these two guys. And so the maximum is this one. We copy here. This tau 6 is the last factor. And we take together this information here. We append here. And we have this instantiation here. So now we have the information. We have not only the probability of the MPE query, that is the MPE probability 0.3390, but we also have the MPE instantiation. They're going to be female for sex, no for the condition, and the two tests are equal with a value not VE. So just to finish this example, so these are the two pieces of information that we got from. So we have the assignment and the probability. Most of the case we are interested in assignment, but in some case we also might be interested in the probability. But in the case that we are interested in the probability with evidence, we need to do one additional step, that is the normalization, because we need to compute what is the probability of evidence first and divide it by the probability of evidence. So what we need to do is to compute this guy here, that is the probability of A equal yes, and I'm going to find out that is 0.7205. And in this case, the probability of the query given evidence will be this guy that we computed as probability of query and evidence divided by the probability of evidence, and it's going to be 0.3390 divided by 0.7205, that equals to this 47% here. So that's going to be the final answer. Okay, so what we have just discussed is also known as the Viterb algorithm when we apply to hidden Markov models, and we have one elimination order pi, that is the elimination of this variable first, followed by this variable, and this variable O2, followed by this, and so on, until we get to the end of the model. So this is an MPE query because we don't have variables that need to be eliminated, because we're going to ask what is the probability of all those variables that we have here, right? So given the evidence that we have here, so the query variables will be all the hidden variables that we have, S1 until Sn. So there will be no variables to be eliminated because all of them are part of the query. If we use this elimination order, we can see that the hidden Markov model reminds a little bit a tree, right? We have no cycles here. And if we have this elimination order that we eliminated this variable and this and this and this and this and this, as we do, doing this forward move, as we learned when we discussed the Viterb algorithm. So the elimination order will have width 1. And that's very good because the computation of the Viterb algorithm is going to be very efficient. So, all right, so it's going to be efficient in terms of space and also time. All right, so I think that is good for this video. We continue in the next one. So I'm going to take a look in a very different approach for computing an MPE that is using systematic search. So see you soon.